This video is for the GCSE in Physics Topic 1, all about energy. Now we start by talking about energy stores. This may be different to how you have learnt about energy before, or how it may be presented in older textbooks, or how it may be presented in videos where the person making the video was taught using those older textbooks. It used to be that we would teach energy types and energy transformations. So we would have things like kinetic energy, chemical energy, but we would also have things like electrical energy and light energy, sound energy, that sort of thing. And we would talk about changing energy from one type into another. That is no longer how it is taught. It's no longer the language that examiners use when they are teaching their GCSE in physics, when they're writing questions, and when they are marking the students' answers. You can sometimes get away with using that sort of language about transformations in energy types because it is a perfectly valid model for energy. It's just not the model that we use nowadays. Nowadays, we talk about energy transfers into and out of various energy stores, and we talk about, sometimes this is called the pathway model. I prefer to call it the energy transfer model. So what does that look like? Well, this is taken from the specification for the 𝗟𝗀𝘀𝘀 GCSE, so there may be small differences if you do a different board, but it looks like this. We have our energy stores, and 𝗟𝗀𝘀 chooses to list 5 energy stores here. Chemical energy, kinetic energy, gravitational potential energy, elastic potential energy, and thermal energy. These aren't types of energy, these are stores of energy. So what does that mean? That means that we place energy into one of those stores. It's as easy as that. So we don't change energy from one type to another, we simply move it from one store to another. Energy is one thing, it's not producing the misconception that there are different types of energy. That's not quite accurate. So energy that's stored by virtue of chemical reactions, in other words, where electrons are and how electrons want to move around, that's going to be referred to as our chemical energy store. If we move energy out of the chemical energy store in such a way that things start moving faster, then we've moved energy into a kinetic energy store. Energy that it manifests as motion, or we should say that there is motion, and we can calculate an amount of energy associated with that motion. And you can see the rest of these here on this list. So position in Earth's gravitational field, that's our gravitational potential energy store. Lift something up, you increase the energy that's stored there. Elastic potential energy store, changing shape. We can think of this as things like springs changing shape. Temporarily is important because the whole point is with a spring, if I release the spring, it will return to its original shape. And thermal energy stores. This is good enough for now. It's to do with the temperature of a body. A body at a higher temperature has more energy in the thermal energy stores. It's not wrong, but we'll go into more detail about that later. You'll notice there are some things missing there. There's no electrical energy, light energy, sound energy, nuclear energy, or an energy store to do with gas being held at a pressure. That is an energy store, but that's not included on this list. Now we have to move energy from one store to another. So how do we do that? We use these methods of energy transfer. Heating. So that is usually we think about in terms of conductive heating, and we'll talk about that in the next video. Transmission of waves, so that's where we could talk about light or sound, but also radiative heating would fit into that category. Electric current, so that is where we think about the role of current in transferring energy from one store to another. And mechanical work being done, force changing the motion of an object, mechanical work being done. So these 4 bullet points in the top right, they are all methods of doing work. That's what we call it. Doing work to move energy from one store to another. And the language here you've got to get used to. Now these diagrams, these are just 2 examples, are energy transfer diagrams used to show how energy flows from one store to another. And in these diagrams, I've started with an energy store and finished with an energy store, but you don't actually have to. You could start with the transfer into the store. So you would start with the arrow, not with the box. I've just happened to have started with the box here. So with a battery-powered lamp, electric lamp, we have energy stored in the chemical energy store of a battery. Then that energy is transferred to the thermal energy store of the lamp. Well, how does it get from the battery to the lamp? Well, there must be a current. If there's no current flowing, for example, there's a switch that's open or something like that, so no current can flow, then there's no transfer of energy from the battery to the lamp. Now, we are not saying that the current is a store of energy. We're not saying that electricity carries energy all along the wires from one place to another. And so you could intercept the electricity at some point along the wire and take that energy out. That's not what we're saying at all, which is good because that's not true. What we're saying is that if there is to be a transfer of energy due to this thing we call electricity, then there must be a current to do that transfer. There must be charge moving. The charge doesn't have to move through the battery, pick up energy, electrical energy, trundle along to the lamp, drop off its electrical energy. That's not how it works. That's just wrong. What does happen, though, is if there is energy transferred into the lamp's thermal energy store, then there must be a current passing through that lamp. Why is there a current? Well, because there's a reduction in the chemical potential energy store within the battery. Now, it's a little bit more complicated than that. We talk about potential differences, and all of that stuff comes up later on in the electricity video. So the arrow here shows the transfer, sometimes referred to as the pathway. I don't like that terminology. The boxes show the energy stored. And notice within the boxes it says chemical energy store in battery. We're not just saying what the store is, we're saying where the store is. So the chemical energy store is the type of store, if you like, and then the battery is where that store is found. Then we have along the arrow the transfer between the stores. In this case, it is the current transferring the energy from this store to this store. And then the next step, we have energy coming out of the thermal energy store of the lamp and going into the thermal energy store of the surroundings. And it's the infrared waves that transfer that energy from the lamp to the surroundings. So the waves aren't themselves a type of energy. That's incorrect. But they transfer energy from the lamp to the surroundings. We also have light waves, and that will also ultimately increase the thermal energy store of the surroundings, but I haven't bothered drawing that store because I'm not really interested in that. I've only drawn some of this diagram. You know, if we wanted to get really fussy, we'd say, well, where did the chemical energy store come from in the battery? Well, there's going to be some sort of chemical reaction going into that, and that could be another example of an energy transfer as a chemical reaction. So this list of 4 energy transfer mechanisms, this list of 4 energy transfers isn't complete. There's more than this. Similarly, this list of stores isn't complete, because we could have the nuclear energy store. There's nothing wrong with having nuclear energy as a store of energy. It doesn't usually get included in this list at GCSE level, so students don't get nuclear energy stores confused with nuclear energy resources. Very similar sounding names, so they just leave it off the stores altogether at this stage. May well come up later when we look at nuclear physics. Here's another example. Gravitational potential energy store of an object. What is that object? Well, the picture shows some deflated floppy ball which doesn't bounce. When we drop this object, we lose energy from the gravitational potential energy store. It goes into the kinetic energy store of the object. And what is moving the energy from one store to the other? In this case, it's a force. And if we can name that force. We don't just say, well, it's a force doing it. We say it's the gravitational force that is doing this work to move the energy from this store into this store. The object is moving, but then it hits the floor and it stops moving. Where's that energy gone? Well, we've gone from having motion, which is nice and regular and organised as the ball is falling, to the atoms jiggling around randomly more quickly than they were before. The motion's all still there, but it's now random motion of the molecules, and we call that, well, that's part of what we call the thermal energy store. So there's a force that stops the object from falling, this prevailing motion of the object, moving the energy from that store into this more random motion store we call the thermal energy store. That is the reaction force from the floor pushing up on the object. That's what stops the object from moving. And we're going to have sound waves. There's going to be a thud sound. They're going to be carrying energy away to where? Well, again, probably the thermal energy store of the surroundings, really. That's another store. That's ultimately where this sound is going to be transferring the energy to, is to the thermal energy store of the surroundings. So things to remember when you're answering questions about energy transfers. Use these 3 bullet points to help you. Okay, what's the store, where's the store, and what's the transfer between the store? So the first example, what's the store? Chemical energy. Where's the store? In the battery. And what's the transfer? Current. You don't have to have the store at the start. You could have the transfer at the start, okay? And some of these diagrams are better than others. This one's not terrible. It's not great, but it's not terrible. So let's look at the next topic. The next topic, so lesson 2, if you like, is conservation of energy. We were moving energy from one store to another. Energy wasn't being destroyed. It's not being created. The same amount of energy leaves a store as goes into the next store. And so this is, we refer to this as as one way of writing, the first law of thermodynamics. This is what you need to memorize. You don't need to know the name of this law as the first law of thermodynamics. You do need to know it's called energy conservation, or the conservation of energy. Energy cannot be created, cannot be destroyed. It's moved from one store to another. You may have seen or heard or read, energy cannot be created or destroyed. It is just transformed from one type or one form to another. That's an older language. It's not the model we use nowadays. Said that before. We use the transfer model. So here's the example of a bungee jumper. Examiners love bungee jumping, it seems. The bungee jumper starts up high, so they have gravitational potential energy store full of energy. Well, not full, that's the wrong word. There is lots of energy in their gravitational potential energy store of the bungee jumper. They then allow the gravitational force to accelerate them downwards, increasing the amount of energy in their kinetic energy store. As they are moving, so I'm not happy with these arrows. I think this air resistance arrow should come off the kinetic energy store arrow. It's not a perfect diagram. Air resistance is caused by motion through the air, so you'd have to have motion for that to happen. So that would be moving energy out of the kinetic energy store. So I'd prefer this arrow actually to be at the end of there, here. But it's not. I've drawn it there because I drew it wrong. So let's draw them there instead. Let's just erase all ink. Where's that air resistance moving energy to? Well, the thermal energy store of the surroundings. The rubber band, or whatever this bungee cord is, extends. The elastic force from that rubber band is going to be reducing our speed and ultimately will stop at the bottom of our descent. So that's moving energy from the kinetic energy store into the elastic potential energy store of the rubber band, or the bungee cord. And again, if we're moving, if the rubber band molecules are moving past each other because it's extending, that is going to cause energy transfer into the thermal energy store of the surroundings. Interestingly, here I've got energy store of the surroundings increasing as the cord contracts. That's not quite true. Actually, that's going to have energy going in the other direction from the surroundings as the rubber band contracts. But we don't need to go into that now. So there's a second mistake on this, which is this part I've circled. Actually, there are internal frictional forces as, well, not friction really, as the rubber band contracts, that's actually going to cause a cooling effect on the rubber. But we'll leave that for now. Okay, it's only a rough diagram to give us an idea of how to lay out the process. Then the kinetic energy stored at the bungee jumper, they're moving upwards, but they're slowing down. They're slowing down as they ascend until they stop ascending when they're at the highest point they can reach. And that's when the energy that's left has been stored back in the gravitational potential energy store. And again, the gravitational force is the one that is slowing them down as they ascend. So this isn't a perfect diagram, it definitely isn't, but you could put it in words, or you could just present it as a diagram. There isn't any energy destroyed, but there is energy leaking out all the way along. We have these thermal energy stores of the surroundings increasing, which means that the total amount of energy in the bungee jumper at the end is going to be less than the total amount of energy in the bungee jumper at the start. So the bungee jumper won't get to the same height when they return to the highest point. They'll be lower down than they were before. This is because we're losing energy from our system. It's not being destroyed, but we are losing it into the surroundings. A closed system is a theoretical ideal system where energy doesn't get transferred out of our system into the surroundings. We'll talk more about how you can get close to a closed system later on in this video. So another example is basically the same example, but in the context of a roller coaster. The cars of the roller coaster chug up this right-hand side, get to the top, and then we fall. The cars fall down the side of this ramp and coast around. There's no motor pushing them around the track. They are coasting. That's why it's called a roller coaster. So the gravitational potential energy stored here, some of it gets transferred to kinetic energy stored here. We've still got some gravitational potential energy. We're still above the ground. It's actually more complicated than that. At A level, we'll go into more detail about how to calculate this energy more formally, more properly, but that's okay for GCSE level. If we didn't have any sound waves radiating out, carrying away the energy into surrounding energy stores, then we would end up ascending back to the, and there was no friction as well, we'd end up ascending back to the same height that we started, but that doesn't happen. It says the total amount of energy in a closed system remains the same. It's not a closed system. Friction is the reason why it's not. So that is how we can understand energy conservation in terms of these energy stores. Let's move on to the next lesson, lesson 3, which is about work being done. And I've mentioned work being done before. We do work when we transfer energy. That's what work done means. The amount of work that is done is the amount of energy that is transferred. Work done is a synonym for energy transfer. So if we are doing work, we can calculate how much work is being done. In other words, we can calculate how much energy is being transferred from one store to another. Now, this equation is the equation for doing work by a force. So if we go back 2 lessons to lesson number 1, remember there were 4 methods of energy transfer. The 4th method here was a force changing the motion of an object. That is what's happening here. This equation is for the force changing the motion of an object, moving energy into or out of the kinetic energy store of a body. If that's what's happening, this is the equation we can use. F and S, those letters are in bold. W is not. That's not an accident I've done that. That's because F and S, the force and the displacement, are vectors, and the work done is a scalar. And I've used a dot for the multiplication between the F and the S. Now, I've put a little note about what I've done there. The dot in this equation means multiply when the product, W, is a scalar. I do cover that later on, but it does go a bit beyond GCSE, but I will cover that later on. So don't worry too much about why I'm using a dot now. It is a particular type of multiplication that returns a scalar. Work done, the amount of energy is a scalar. It doesn't have a direction. So if we're doing work on an object by a force, then we are increasing the kinetic energy store of the object. We do work on it, it's going to go faster. We're increasing the kinetic energy store. That's the sort of language that we use. F and S have to be in parallel directions. So if F and S are in the same direction, in other words, I'm displaced forwards whilst I'm being pushed by a force forwards, that's going to cause me to go faster in that direction. That increases my kinetic energy. So that's work being done on the object. If the force and the displacement are in opposite directions, so I'm being pushed forwards, let's do it the other way around. I'm moving forwards but being pushed backwards, that's going to cause me to slow down. That's going to decrease my kinetic energy. That is going to mean that work is being done on me to remove, work is being done by me to remove my kinetic energy. If work's done on me, then it increases my kinetic energy. So if the forces are and the displacement are in perpendicular directions, actually no work is done at all. So an example of this might be a waiter pushing a tray of drinks up as they walk along. They're pushing it up, gravity's pulling it down, but they aren't actually doing any work on the drinks when they push them up because the drinks are moving horizontal as they walk to your table. So the drinks don't get any faster or slower because of the force of the person pushing. Well, maybe that's a bad example because the gravitational force is going to be equal in magnitude to their push force because it's in equilibrium. The drinks are in equilibrium. So maybe that's not such a good example. I'll think of a better one. When we start talking about interactions between bodies in 2 dimensions or 3 dimensions, then that becomes a little bit more useful, perhaps. So here's our old energy transfer diagram again. This is for a vehicle with brakes. If we've got energy in the kinetic energy store of the vehicle, of the car, the force of friction between the brake discs and the brake pads causes energy to be transferred from the kinetic energy store of the car to the thermal energy store of the brake pads and the brake discs. And I've just put into words here. You can read that yourself. If you want to pause the video and read that yourself, you can do. I put into words there what's going on when the car brakes and how you use this equation, or how you could use this equation to calculate the amount of energy that's transferred. It's always worth practicing these equations and using them. And you can do that with the drill spreadsheets, which are on my website for those who are enrolled in my tuition sessions. Or you can buy them off TES if you do a search for my drill spreadsheets, Physics with Keith drill spreadsheets. But then there's loads of good questions on Isaac Physics. You don't have to buy my stuff. You could just use Isaac Physics questions and get lots of practice doing stuff with this equation. Lesson 4 then, we're looking at gravitational potential energy stores. Now this is the equation, I'll start down here on the bottom right. This is the equation that we start with, the equation we saw last lesson. Now we're going to use that to come up with an equation to calculate how much energy has been passed into or out of the gravitational potential energy store as a body ascends or descends. That's what we're going to do. So let's have a look at this equation. If we are talking about gravitational potential energy stores, then the force we're talking about is the gravitational force. And another name for the gravitational force, particularly when you're looking at an object on a planet like the Earth or on the Moon, we might talk about the weight of the object. So I've replaced the force with the word weight. That's all I've done there. I've replaced the F with the word weight. What else have I done? Well, if we're talking about gravitational potential energy stores, we're talking about ascending and descending. Our displacement is a vertical ascension or a vertical descension. Is that a word? Descent. Descension might not be a word, so, although it should be. So S is our displacement. Yeah, it can also be thought of as our difference in height. If we ascend, our difference in height is a positive one. If we descend, our difference in height is a negative one. So we can use that little triangle delta to mean a difference. That's the Greek letter delta, capital delta. and it means a change in. So we're changing the height of the object. That is changing its position. That is a displacement of the object. You should have covered displacement as a vector during Key Stage 3. You might not have done. Don't worry if you haven't. It does come up later on in the GCSE. So here we go. This is just our work done, but the work is moving energy into or out of the gravitational potential energy store, then instead of calling it W for work, we could actually just call it delta, the change in, EP, the energy that's in the gravitational potential energy store. Sometimes we won't bother putting the deltas, so you might see E equals weight times H. That's fine. I'm putting the deltas in here because it is actually more correct. When you do A-level, you'll see why that's much more correct. But as you're using the equations, it doesn't really make much difference. Note here that we're talking about weight, not mass. So this is a fundamental mistake that younger students often make. They confuse weight with mass. They are not the same thing. Weight is a force, the force of gravity. It says on Earth, but you can also refer to someone's weight when they're on the moon or on any planet. But weight is the gravitational force. Weight is not mass. So if I want to take this equation and instead of weight, I want to write it in terms of mass, I need to know how to calculate weight when I know mass. Well, weight is mass times the gravitational field strength, which on the Earth, AQA takes it to be 9.8 newtons per kilogram. Other exam boards use different figures. So check whether your exam board uses 9.8 newtons per kilogram or 10 newtons per kilogram. It's important to check these things. So that is our equation to calculate the weight when we know the mass. Weight is mass times g, where g is the gravitational field strength. Also, don't just call it gravity. Don't say weight is mass times gravity. I have seen that out there in the wild. Don't say that. The word gravity is too vague. If we can avoid the word gravity altogether, we'd be happier. Gravitational force, gravitational field strength, gravitational potential energy. Any one of those you could think of as gravity. So don't use the word gravity. Not by itself. So let's replace the weight with mass times g, mass times the gravitational field strength, and you end up with this equation here. I've dropped the dot just because usually the dot isn't included when this equation is written down by examiners. So I've dropped the dot, but it technically is still a dot in the middle there, indicating a particular type of multiplication where g and h have to be along the same direction. In other words, gravity acts down, and your change in height is a vertical change in position. So g and h are parallel to each other. So you could put the dot in there. So there we are. That's E equals mgh, as it often gets stated. You need to memorize that equation, just like you've got to memorize the work done equation on the bottom right. And you've got to memorize how to calculate the weight of a body if you know its mass. You've got to memorize these things. There's a bit here about what happens as you increase the height of a body, you increase the energy stored in the gravitational potential energy store of the body. It's a bit of a mouthful, but it's better to get the right language. Don't just say it gains gravitational potential energy. You can get away with it, you probably get marks for it, but it doesn't show clear thinking. Clear thinking is about energies moving from one store to another. So weight acting down the whole time. This is a ball that's bouncing like this. And it doesn't matter which position you choose. This is the same ball that's bouncing, a stroboscopic photograph or something. It doesn't matter which position you take. Gravity's acting down. The ball is being pulled down by gravity, attracted towards the centre of the Earth. So the g is down in all of these. That's just the way it is. As the ball ascends, gravity acting down, the weight acting of the object is down, the body is ascending, so it's moving upwards. So F and S are in opposite directions. So the work that's being done is reducing the kinetic energy store of the ball and increasing the kinetic energy store. Okay, we're moving energy out of the kinetic energy store and into the gravitational potential energy store for the ball. I hope I said that right. Then we're at the top height here. the kinetic energy store of the ball is at the minimum it's gonna have. The gravitational potential energy stores at the maximum. It's not then it starts being pulled down. It's being pulled down the whole time, this ball. So the force acting on the ball is still down, it's still down, it's still down, but now it's being displaced downwards as well. And so because F and S are parallel to each other, we're going to increase the kinetic energy store of the ball by decreasing the gravitational potential energy store of the ball. We're going to move energy from the gravitational potential energy store to the kinetic energy store. There is another equation we could use here, which I'll just write in this horrible red pen on the board. What we could do is No, I won't share that equation now. I'll share that equation when we look at power in just a little bit. I won't share it now, because otherwise it's going to get confusing because we haven't covered power yet. Lesson 5. So in Lesson 5, we introduced two new equations. The one at the bottom, hopefully you will have covered this in Key Stage 3 for stretching springs. This is Hooke's law. Hooke's law tells us that the force applied to a spring is directly proportional to the extension of the spring. So if I plot a graph of force applied to a spring versus the extension of the spring, we get a straight line, well, up to a certain point. But let's just look at the straight part for now. Hooke's law comes up later on. It's like building a sort of a house of cards here, where you've got to hold the cards, not just one card, but two cards, maybe three cards at the same time to make the stable structure. And if you take one of those cards away, the whole house of cards falls down. It's the same thing with physics. I can't teach about energy in elastic potential energy. Sometimes it's actually usually just called elastic energy store. I can't teach about elastic potential energy, elastic energy, without also talking about Hooke's law and the spring constant. But Hooke's law and the spring constant, that comes usually in the section about forces, which is done later on. So hopefully you've covered this in Key Stage 3. If not, hold it lightly and we will cover it again when we're looking at forces later on in this video series. So F equals Ke, where K is the spring constant. It's a constant of proportionality between the force that is stretching the spring and the extension of the spring. It is the gradient of this line. That's what K is. The higher the gradient, the steeper the line, the stiffer the spring is. In other words, I need more force to get the same extension if this line is steeper, if the spring is stiffer. When measuring E, just remember you're measuring extension from when no force is applied to when a force is applied. It's not a case of if I apply more force, I measure the extension from the previous force to the new one. No, it's always measured. The extension is always measured relative to when no force is applied to the spring. Okay, so these two equations, we could derive them. I might do a video where I derive them at a later point. I'm not going to do that now. This one here, the bottom one, so the middle one on this page, this one here, elastic potential energy store, I think is an easier one to derive because what we're doing is calculating the area of this yellow shape, and because work done is force multiplied by extension, that is an area of this yellow shape, which is a triangle. Half base times height is where the half comes from. So you end up with a half times F times E. And because F is Ke, we end up with a half times Ke, which is F, times E, hence you get half Ke squared. I'm not going to go into that derivation and write it all down and things, because you don't need to know it for your GCSE, but I will produce a video where I derive all these GCSE equations just for the fun of it and for completeness, and I'll upload that at some later point, hopefully over this summer. Similarly, the equation for kinetic energy stores, I'm not going to derive that. It involves plotting a graph of perhaps momentum versus velocity or something like that, but I'm not going to go into that now. Or you can do it in terms of mechanical force and displacement. It doesn't matter. We'll do that at some other point. So you have to memorize the top equation, but you get given the middle equation. Oh, and you have to memorize the bottom equation. So because you get given the middle equation, which allows you to calculate the elastic potential energy store, or the elastic energy that is stored, it's the same form of equation. Half times a constant times the thing that's changing squared And for kinetic energy, half times a constant times the thing that's changing squared. You increase kinetic energy by speeding up, and you increase the energy stored in a spring by stretching it. So that the equations take the same form. So if you forget half mv squared, just look at half ke squared on the formula sheet and it will remind you. Again, you can practice these equations using Isaac Physics or using my drill spreadsheets. It's worth practicing these things. Moving on to lesson 6, energy dissipation. So we've seen already that energy is always conserved, but that doesn't mean that you're always able to transfer it from one store to another, because once it's spread out, it becomes wasted. We can't use it anymore. It's wasted energy. So this box here, the more spread out the energy is, the less useful it is. So there's some key words we need to define. Useful. So a useful energy store is one where we're transferring energy into a store, which is what the appliance or device or whatever it is that's transferring energy, the transducer, whether it's transferring energy in the way that the appliance was intended. And we can talk more about that in a later lesson. Wasted energy is transferring energy in a way that's not useful. Usually that means into the thermal energy store of the surroundings, usually. And as you can see, you can't turn friction or frictional forces like air resistance off. You can't turn them off. So as long as these forces are acting, these forces that oppose the direction of motion of the body, these forces that are opposing motion, there's always going to be work done by those forces transferring energy into the thermal energy stores. That means that energy is going to be dissipated. Energy is going to be spread out, technical word, by those frictional and friction forces. And of course, the more spread out it is, the less useful it is, the more wasted it is. So frictional forces do work to reduce kinetic energy. Always reduce kinetic energy stores in a body. And that will always cause an increase in temperature of the surroundings. So we've got this lovely picture on the bottom right. This is a geyser, I think this is Yellowstone National Park, spewing hot water out. And we can use that hot water for whatever we want to use it for. If you lived in Iceland, you might have hot water supplied directly from heating water by passing it through the hot rocks underground. But here's the hot water in the USA, in California, I think it's California, the Yellowstone National Park, spewing this hot water out the ground. And you can see from this thermal photograph that all around, thermogram, all around the area is now hotter. Well, I can't use that energy once it's spread out. I can't gather all that heat, whatever that means. I can't gather it all together again and use it again. Once it's spread out, it's spread out. And the second law of thermodynamics tells us that we will always transfer energy from high temperature bodies to low temperature bodies by heating. There are ways of going against that, but it involves actually doing a lot more work to go against that. So apart from things like refrigerators and freezers, which are a separate interesting case, and you should definitely look into them, in general, we could say that energy is transferred from high temperature bodies to low temperature bodies by heating, which means that eventually everything's going to be the same temperature. All the energy is going to be as spread out as possible. And physicists, astrophysicists have calculated how long that's going to take to happen. It is 1, 6, 0, 0, 0, 0, so 1, 6, and 105 zeros. It's a very, very long time, number of years. 1, 6, 0, 0, 0. I'm not going to count all those zeros years. That is when all of the energy would be so spread out that nothing useful can happen anymore. No work can be done, nothing can happen. We refer to that as the heat death of the universe. It is inevitable, it is coming, but it is a long way away. Oh, by the way, you don't need to know this is called the second law of thermodynamics, but you do need to know it, and we'll cover it in more detail in the next video where we talk about thermal energy in more detail. Right, so if we lose energy to the surroundings by increasing the thermal energy store of the surroundings, and that's wasted energy, what we really want to do is reduce that wasted energy as much as we can. This topic is all about energy and efficiency. And usually we want to improve the efficiency of whatever appliance or machine we are using. The top right shows the equation we use to calculate the efficiency of an appliance or of a machine or of a transducer. So we've got the bottom here, the energy that is input into our appliance, and the top is the energy that is transferred out of the appliance into a useful store. So for a toaster, for example, we want to increase the energy in the thermal energy store of the bread. For a kettle, we want to increase the energy in the thermal energy store of the water. For a electric car, we want to increase the energy in the kinetic energy store of the car. That's useful. That's the useful energy store, the destination of the energy into a store, which is what the appliance is designed to do. Input energy is the total energy that comes in, which is also the total energy that comes out. Okay, because energy is conserved. But the energy that comes out, and it could come out by going into a different store, of course, well, it will do, but the energy that comes out, some of it will be useful, going into a useful energy store, some of it will be going into a wasted energy store. The total energy going to the wasted energy stores plus the total energy going into the useful energy stores is equal to the total energy that's gone into the appliance. That's conservation of energy. First law of thermodynamics. So this is efficiency, and I use this Greek letter epsilon for the efficiency. A lot of people just write the word efficiency. You could present it as a decimal. There's no units because the joules on the top of this fraction and the joules on the bottom, the joules on the numerator and the joules on the denominator, they cancel out. So there's no units. You could present efficiency as a percentage by multiplying this by 100%. Okay, so that's quite a common thing to do. 0.50 efficiency is equal to 50% efficiency. When we talk about higher or lower efficiency, it doesn't just mean we get more or less useful energy out, by which I mean energy output into the useful energy stores. That's not enough. It's to do with the proportion of the total energy that's transferred by the device into the device, the proportion of that that's transferred usefully. That's what we mean by higher efficiency, and lower efficiency would be a lower proportion. Okay, so what do we mean by proportion? It is the useful energy transferred divided by the total energy that is transferred. Okay, higher efficiency, more useful energy out, divided by total energy in. You're just using this equation. If you're asked what it means to be more efficient, just use that equation and say it means we get more useful energy out, divided by total energy in. But don't forget the last part, divided by total energy in. It's a very common thing that students forget. They think more efficient, more energy out. Well, yeah, for a given amount of energy in. So how do we improve the efficiency of something? Okay, so let's move down to here. Wasted energy we've talked about. Total energy transferred is sometimes called I've talked about that. So how do we improve the efficiency? Well, it depends on the way that energy is being transferred into the wasted energy store. So, for example, usually it's friction between moving parts in a machine. What do? We lubricate the parts of that machine, reducing friction. That reduces the work done by friction, reducing energy transferred, reducing the proportion of energy transferred into the wasted energy stores, thermal energy. Resistance in a wire. So if we have current passing through a wire, we want the current passing through the appliance to transfer energy to the appliance. But the wires itself also have current passing through them. So that means there's going to be energy transferred to those wires as well. That's a nuisance. We don't want that. Now, there's ways around that. We can get rid of the wires and do purely wireless energy transfer. Yeah, that's, what we get coming from the sun, infrared radiation coming to us, visible light coming to us from the sun is pure wireless energy transfer. And you put something in between and get the particles to oscillate, and now we're transferring energy into those particles. I'm not talking about that. We're talking about traditional circuit with wires. In a traditional circuit with wires, we need to reduce the resistance of those wires to reduce the heating effect of the current passing through those wires. You should have done electricity, current, resistance. You should have done that in Key Stage 3. Again, if you haven't, don't panic. I believe that's video 4 or 5 that comes up. So it will come up soon. Air resistance. Air resistance causes heating. How do we reduce air resistance? We streamline any vehicles moving through the air. And there's rattling parts, radiating sound waves. Radiating means giving out. Radiating out those sound waves. That's going to be transferring energy to the surroundings. So what do we do to stop that happening? We tighten up the loose parts to reduce the vibration, reduce the rattling, improve the efficiency of our machine. Here's the penultimate lesson for this topic. So 1.8, appliances. There's not a lot in this, to be honest with you. When I teach this, I ask my students if they can identify all the different appliances here. I can't. I recognise things like a kettle and a microwave oven and probably a fridge freezer. Maybe that's an air fryer. I don't know. Maybe that's a coffee grinder. I don't really know. Is that a food processor? It looks like a toasty maker. What have we got over here? A blender, maybe? I don't know. I don't know what half these appliances are. They all look the same to me. An oven. I know there's an oven there. There might be an integrated dishwasher somewhere in one of the cupboards. I don't know. Doesn't matter. I show a home, a kitchen like this, a very modern home, a very middle-class home with lots of lovely appliances. And we talk about what the useful energy transfer by that appliance is. And it's usually either into the thermal energy store of the food or into the kinetic energy store of the food if it's a mixer. And then we talk about what the wasted energy store is. And it's often things like transferring energy into the surroundings, not actually into the food. We can improve the efficiency by insulating the oven and things like that. So I'm not going to go through this too much. This is just talking about typical appliances. I mean, you wouldn't find a hairdryer in the kitchen, but typical appliances. There's a reminder here that electrical energy is not what we talk about. Current transfers energy from one store to another. And then we've got this lovely bit up here where it talks about, well, we're talking about energy coming out of appliances in our home. How do we get the energy in the first place? Well, so most homes are connected to the national grid. That's how we get our electricity, whatever that means. A lot of houses are connected to a gas supply. I say houses, they don't have to be houses, any sort of homes here. Because if you live in a caravan or something, then you might have canisters of gas delivered instead of being hooked up to the mains, or you might be hooked up to the mains. Some homes have a renewable power supply. I'm very lucky in my house. I do have solar heating panels on the roof of my house, which warms the water up. But they're different energy stores, energy ways of transferring energy into the home there. And last topic, the last one, the last lesson from this topic. Lesson 9, energy and power. So we've got a new equation here. This is an equation you need to memorize. Power is energy divided by time. That is what we mean by power. Power is a technical word. Okay, I know colloquially we have all sorts of meanings for the word power, just like we do for the word energy. But in physics, it means something in particular. This is what power means, the rate of doing work. The rate of doing work. Wasted power, input power minus output useful output power. We've talked about that in terms of energy. It's also true in terms of power. So if we have our efficiency equation from before, where we had energy that is useful, I'll put EU rather than writing out full, and energy that is input, EI, like that. Well, if I were to divide the energy that's useful by time, and I were to divide the input energy by the same amount of time, okay, I haven't changed that equation because I've divided the numerator and the denominator by the same number. But now instead of the useful energy, using this equation here, I've now got the useful power. Instead of the input energy using this equation here, I've got the input power. And that's how we end up with this other equation for efficiency. But just like with the first equation for efficiency, efficiency can be presented as a decimal or as a percentage. Don't write it as a fraction. A fraction is a half-finished answer. The examiner wants you to give a decimal or a percentage. Don't mix up energy stores and energy transfer methods. Don't get the two confused. Keep them separate. These are the 5 stores. These are the 4 transfer methods. Yes, there are more. Let's just start with those. And to give you an indication of what these numbers represent, these are some typical powers in watts, so you get a kind of idea. This is electrical lamp, 20 watts. Yeah, it might be somewhere as low as 10, could be as high as 60 watts. Cooker, 10,000 watts. Yeah, probably more like 5,000 watts. It gives you a ballpark idea, order of magnitude number, to tell you roughly what that energy feels like. Just a note about writing big numbers. Notice that I've grouped the zeros into 3s. This is very typically done. This is actually the ISO standard. Can't remember the ISO number, but it's the standard. Don't use commas to separate thousands, to separate 3 zeros, because in most places in the world, a comma is used as a decimal point, a radix point, so don't use a comma for that. Instead, group them with a half-width space between each group of 3. So here we have the reason for it. If this is watts, then 3 zeros would be kilowatts, then it would be kilo, mega, giga, tera. This is 10 terawatts. It's very, very quick and easy to... This order of magnitude is probably more than that, but it's very easy to work out. So here we go. We've got kilo, mega, giga, tera. What comes after tera? Peta. I can't remember. Okay, I don't even know it goes up that high. But let's go with peta, and I could say this is 1,000, million, billion, 100 billion petawatts. There we are. Very, very quick to make the numbers expressible in a sensible way. Also makes it less likely you're going to count the zeros wrong if they're grouped in 3s. And that is the end of the topic of energy. In the next video, we will be looking at the topic of energy transfers into and out of thermal energy stores. We're looking at thermal energy in more detail. And then the video after that, we'll be looking at energy resources. I intend to cover the whole of the GCSE in this video series, 16 videos. These are going to be available for everyone, but they are designed to accompany the tuition sessions I offer every week. They are interactive, unlike these videos. They are live, interactive sessions every week during term time, where students can ask questions, I'll answer them, I'll ask questions, they can answer them. There's an interactive whiteboard where students can write answers. I can see what they're writing, but the students can't see each other's. It's online lessons, or online tuition. Done right. It's done very well, I think. It's very affordable as well. Go to physicswithkeith.com and have a look if that's something you'd be interested in. I'm offering it for GCSE Physics, but also GCSE Astronomy. This is new for me at the time of making this video. I hope you found that useful. My name is Keith. I am a physics teacher in one of the top grammar schools in the country. I've fully qualified with PGCE, QTS. I've got my master's degree in physics. Teaching for way over a decade, 15 years or something now. Teaching for a very long time. Examiner for AQA, so I know how exams work, what the examiner's looking for, how to interpret mark schemes properly. What else could I say? I'm an Isaac Physics ambassador as well. Wrote lots of resources for the Isaac Physics project, which is all free. You can go online and find Isaac Physics. It's all free. I thoroughly recommend it. So if you're interested in what I offer, I'm not going to say like and subscribe because that's cheesy, but do have a look at my website, physicswithkeith.com, and see if that's something you'd be interested in. Take care, and I'll see you in the next video.